Hey, welcome to the Explainer. Today, we are cracking a classic coding puzzle. You know the kind. It seems simple on the surface, but has a really clever solution. We're talking about finding duplicates that are hiding just a few steps away from each other. Let's dive in.
So imagine this. You're checking people into a big event. You need to know if someone's already signed in, but you only really care if they try to sign in again, like within the last 5 minutes. How would you check that fast? Well, that's pretty much the core of the puzzle we're going to solve today.
And here's how we're going to break it all down. First, we'll get to know the puzzle itself. Then, we'll decode its rules. After that, we'll find the absolute perfect tool for the job. Map out our game plans step by step, and then see it all come to life with a real example. And finally, we'll talk about the big takeaway you can use on other problems. Okay, let's give this thing its official name. We're tackling a popular problem from LeetCode called Contains Duplicate 2. Now, the name sounds kind of straightforward, right? But as you're about to see, the real challenge is hiding in the details. So here it is, the official challenge. We're given a list of numbers and a special number k. Our job is to return true if we can find two numbers in that list that meet two very specific conditions at the same time. One, the numbers have to be identical. And two, the distance between their positions, their indices, has to be less than or equal to k. Both have to be true. So before we even think about writing code, let's really make sure we've got these rules down cold. I promise you, getting this part right makes everything else so much easier. Let's just put it plainly. Condition 1, nums of I equals nums of j. We need a match, the exact same number showing up more than once. Condition 2, the absolute difference between their positions, I and j, is less than or equal to k. So it's not enough for it to just be a duplicate, it has to be a nearby duplicate. That k is our definition of nearby. You know, nothing makes rules clearer than a few good examples. Look at that first one. We've got two ones. One's at index 0, the other's at index 3. The distance between them? It's 3. And since k is 3, that fits our rule. 3 less than or equal to 3. So we get true. Now check out that last example. We have duplicate 1s, 2s, and 3s all over the place, but none of them are within 2 spots of their twin. So the final answer is false. That k value changes everything. All right, this brings us right to the heart of the matter. As we're walking through our list of numbers, how do we efficiently remember what numbers we've already seen and, just as importantly, where we saw them last? Well, we could do this the slow way. For every single number, we could loop back through all the numbers that came before it to check for a match. But wow, that would take forever on a long list. The fast way is to have some kind of system with a perfect memory, something we can just ask, hey, have I seen this number before? And get an instant answer. And that perfect memory system, it's called a hash table, or a dictionary, or a hash map. You'll hear a few names for it. It is the perfect tool for this job. I love the coat check analogy. You give the attendant your coat, that's our number. They give you back a ticket, that's its position, its index. Later, when you need your coat, you don't search the whole room. You just use the ticket. It's incredibly fast. Okay, so we have our ultimate lookup tool, the hash table. Now let's build our game plan. This is our algorithm, the simple, plain English logic we're going to follow before we write a single line of code. The logic here is actually pretty simple and elegant. First, we create an empty hash table. Let's just call it D. Then we start walking through our list of numbers, one by one. For each number, we ask D a simple question. Have we seen this number before? If the answer is yes, we do a quick calculation. Is the distance between our current spot and the spot D remembers less than or equal to k? If it is, boom, we're done. We return true. If not, we just update our hash table with this new, most recent location for that number and keep on walking. All right, theory time is over. Let's actually watch our game plan work its magic on that first example we saw. This is where it all clicks. Okay, so here's our setup. Our input array is 1, 2, 3, 1, and our special distance k is 3. We're going to keep a close eye on our hash table D as we loop through these numbers. So we start, and our hash table D is completely empty. The very first number is 1 at position 0. We ask our table, hey, have you seen a 1 before? The table's empty, so of course not. So we add it. We tell our table, okay, remember this. The number 1 was seen at position 0. Moving on. We're at index 1, and the number is 2. Same question to our table. Have you seen a 2? Nope. So we add that information. Now our table's memory holds two facts. One is at index 0, and 2 is at index 1.
And we follow the exact same logic for our third number. We're at position 2, the number is 3. We do a quick check with our table. Seen a 3 before? No, we haven't, so we add it. At this point, our hash table has a perfect memory of those first 3 numbers and where we saw them.
And here it is, the aha moment. We're now at the last number, at index 3. The number is 1. So we ask our first question, is 1 in our hash table? Yes, it is. The table instantly tells us, yep, I last saw a 1 back at index 0. Okay, now for the second crucial check. Is the distance, which is our current index, 3, minus the stored index, 0, less than or equal to k, which is 3? Well, 3 minus 0 is 3, and 3 is less than or equal to 3 is absolutely true. We did it. Both conditions are met. We can stop right here and return true.
So we solved the puzzle, which is great. But honestly, the most valuable part of this whole thing isn't just the answer itself. It's understanding why the strategy is so incredibly effective. This solution is just wicked fast. We only make one single pass through the list. In computer science terms, that's called ON time complexity. It just means the time it takes grows in a straight line with the size of the list. Super efficient. Now, we do use a bit of extra memory for our hash table, but that's the trade-off that buys us this incredible speed. And that leads us to the real golden rule here. Whenever you're faced with a problem that boils down to, have I seen this thing before? Your first thought should always be a hash table. It is an absolute game changer. Seriously, once you start looking for it, you'll see this pattern of remembering the past show up everywhere in programming. It's amazing how we can solve problems that seem really complicated with an elegant, speedy solution, just by using the right tool to remember things. Thanks for digging into this with me.